Now that we've talked a little bit about logarithms and how we convert between the logarithmic and exponential form of an equation using the general log rule, we want to talk about a couple of other important things that we see happening with logarithms all the time related to the base of the logarithm. For instance, it's really common for us to deal with logarithms with a base of 10. So in the previous section, we looked at something like this. We had, for example, log base 8 of 64 is equal to 2. And in that case, the base of the logarithm was 8. Well, here we're talking about when the base is 10, which you'll see happen really commonly. Because it is so common, we actually call log base 10 the common logarithm, and we very often abbreviate it just by not even writing the 10 at all, but instead just by writing log. So if you see, for example, log of 100 is equal to 2, and there's no base written at all, you know that you're dealing with the common logarithm and that the base is 10, it's just implied. It's just a shorthand way of writing the logarithm. If it's a log base 10, we deal with them so often that it would be kind of redundant to not have a shorthand version and have to write log base 10 all the time. But the way that we solve these is going to be the same as the way that we solved logarithms in the last video. We just know that the base is an implied 10, and so this logarithm is telling us that if we raise the implied 10 to the power of 2, we get 100. Or using the general log rule to convert it to its exponential form, the base 10 raised to the power of 2 is equal to the argument 100. 10 to the 2 is 100. We know that's true. 10 squared is 100. We get 100 equals 100. So this is a true equation, and it just tells us that log base 10 of 100 is equal to 2. And if it is the common logarithm, you don't have to read out the base of 10. We can just say log of 100 is 2, and we know that when we say log of 100, what we really mean is that we're talking about the common logarithm. Log base 10 of 100 is 2. We also very commonly deal with what's called base e. E is actually called Euler's number, and it's a specific number like pi. So remember that pi was approximately 3.14159, and it's a non-repeating decimal that goes on forever. Well, E, Euler's number, is the same way. It's approximately 2.71828818. It is a non-repeating decimal that goes on infinitely forever. And it's really common for us, if we're just rounding, to abbreviate the value of E as about 2.7. But when you have a logarithm with base E, so for instance, if you have log base E of x, let's say the argument is x, this log base E we actually call the natural logarithm. So in the same way that we called log base 10 the common logarithm, log base E is the natural logarithm. And what we do is we actually change this whenever we have log base E. We write it as the natural logarithm abbreviated as ln. So log base E of x is the same as ln of x, or the natural log of x, or the natural logarithm of x. So as you continue to work with logarithms, it's going to seem like you have two different kinds of logs. You're going to have log where you have log written out log, and you're going to have natural logarithms written out as ln. But these aren't really two different kinds of logarithms. It's just that the natural logarithm has a base of e, versus this kind of logarithm has any other base other than e. It might have base 10, it might have base 8, it might have base 2. But whenever the base is e, we convert that or rewrite it as a natural logarithm. And of course, since the base is e, something like a natural log of 54.598, if we had that, is basically saying, to what power do we have to raise e in order to get 54.598? Well, we know that e is about 2.7, and so we're saying, to what power do we have to raise about 2.7 in order to get about 55? It turns out the value here is 4, so approximately 2.7 to the fourth power is approximately 54.598. So the value of x in that case is 4. In other words, the natural log of 54.598 is equal to 4. So really, what we want to realize is that with base 10 or base e, we're not really doing anything different than this standard kind of logarithm we're used to, log base 8 of 64 equals 2. With base 10 here, we still have log base 10 of 100 is 2, or with log base e here, we still have log base e of 54.598 is equal to 4. The only point we're trying to make is that a base of 10 is very common, and a base of e is very common. Base 10 is called the common logarithm, and because it's so common, we just abbreviate it by skipping writing the base, and we just write log of 100 equals 2 without the base 10. And base e is important, so we give it its own notation. We call it the natural log, and so instead of writing log base e, we simply write the natural log ln when we want to indicate that we have the base e. Now really quickly, let's go ahead and talk about some restricted values of the logarithm, whether we have the natural logarithm, the common logarithm, or any other kind of logarithm. When we have a logarithm like this, log base a of y equals x, there are some restrictions we have to put on the values of the different unknowns in this logarithm. For instance, when the base is a, and we have a logarithm in this form, we have to keep a greater than 0 and not equal to 1. So that means a can be any positive value greater than 0, can't be equal to 0 itself, but it can be any positive value greater than 0 except the value of 1. So any positive value other than 1. And the value of y, the argument of the log function, because of these restrictions we put on a, y will always be greater than 0 as well. Now the reason that we have these restrictions is just to make sure that we don't end up with any equations that aren't true. In other words, that we basically don't break the rules of math. For instance, if we allowed a to be equal to 1, and we'll just look at this particular restriction here. So if the base a is 1, and we plug that into our log function here, using the general log rule to convert this to the exponential form, we know we have the base a, which we're saying is 1, raised to the exponent, which is x, is equal to y. The problem here is that no matter what value we put in for x, we're always going to get the same result for y. So what you can see here is that if we have 1 to the 0, we get 1, because anything raised to the 0 power is 1. If we say 1 to the first, that's equal to 1. 1 to the second is equal to 1. 1 to the third is equal to 1. You get the idea. So we're changing the value of x, but the value of y is staying the same, which means that if we go ahead and write these back in logarithmic form, if we say log base 1 of 1 is equal to 0, log base 1 of 1 is equal to 1, log base 1 of 1 is equal to 2, log base 1 of 1 is equal to 3. Well, this is impossible. We have the same expression over here on the left, log base 1 of 1, and we're saying that can be equal to 0, it can be equal to 1, it can be equal to 2, it can be equal to 3. This same value on the left can't be equal to all these different values on the right, and these equations still be true. So what we're showing is that if we allow a to be equal to 1, if we allow the base of the logarithm to be equal to 1, then as we're working with logarithms and we're converting back and forth, we can run into some problems where we break down the laws of math and we end up with something that just can't possibly work. And so it's these kinds of issues that we're avoiding when we put these restrictions on the values in this logarithmic equation. So the point here is just to remember that when you have this log base a of y equals x, we just want to make sure that we always keep the value of a positive and not equal to 1. And when we do that, automatically the value of y will have to be positive as well.